Tutorial number 3, Defining Lambda++, Lesson 2. In this lesson we start another semantic definition of Lambda++, which follows a style based on environments instead of substitution. In terms of K, we will learn how easy it is to add new items to the syntactic category of computations K, even ones which do not have a syntactic nature. An environment binds variable names of interest to locations where their values are stored. The idea of environment-based definitions is to maintain a global store mapping locations to values, and then have environments available when we evaluate expressions telling where the variables are located in the store. Since Lambda++ is a relatively simple language, we only need to maintain one global environment. Following a similar style like in IMP, we place all cells into a top cell T. Recall that PGM is where the program is placed by krun after parsing. So the program execution starts with an empty environment and an empty store. In environment-based definitions of lambda calculi, lambda abstractions evaluate to so-called closures. A closure is like a lambda abstraction, but it also holds the environment in which it was declared. This way, when invoked, a closure knows where to find in the store the values of all the variables that its body expression refers to. We will define the lookup rule shortly. Let us not forget to add the closure construct as one for values and the values as k results. Here is a rule of thumb. Whenever you have any stringless attributes, you should also define some k results. Invoking a closure is a bit more involved than the substitution-based beta reduction. We need to switch to closures environment, then create a new binding for closures parameter, then evaluate the closures body, and then switch back to colors environment, which needs to be stored somewhere in the meanwhile. I prefer to add all of these with one rule. Therefore, we atomically do all the following. Switch the computation to closures body followed by a color environment recovery task env of rho prime. Generate a fresh location end, bind x to n in closures environment and switch the current environment rho prime to that one, and write v at location n. This was the most complex k rule we've seen so far in the tutorial. Note, however, that this one rule achieves a lot. It is in fact quite compact considering how much it does. Note also that everything that this k rule mentions is needed also conceptually in order to achieve this task, so it is minimal from that point of view. That would not be the case if we used instead a conventional rewrite rule, because we would have had to mention the remaining store, say sigma, in both sides of the rule to say that it stays unchanged. Here we just use ... Unlike in the substitution-based definition, we now also need a lookup rule. This rule speaks for itself. Replace x by the value v located in the store at x's location n in the current environment. The only thing left to define is the auxiliary environment recovery operation. When the preceding expression becomes a value, env of rho replaces the current environment to rho and dissolves itself. Before we compile, let us make this rule and the lambda evaluation rule structural, because we do not want these to count as transitions. Let us now compile and fail. Compile lambda gives a parsing error saying that v does not fit there in the closure invocation rule. That's because val and exp are currently completely disconnected, so k rightfully complains that we want to apply a value to another one because application was defined to work with expressions, not values. What we forgot here was to state that exp includes val. Now everything works. But it is a good time to reflect a bit. So we added closures, which are inherently semantical entities, to the syntax of expressions. Does that mean that we can now write lambda programs with closures in them? Interestingly, with our current definition of lambda, which purposely did not follow the nice organization of IMP into syntax and semantic modules, And with case default parser cast, you can. But you are not supposed to speculate this. In fact, if you use an external parser, like many languages require, that parser will reject programs with explicit closures. Also, if we split the lambda definition into two modules, one called lambda syntax containing exclusively the desired program syntax, and one called lambda importing the former and defining the syntax of the auxiliary operations and the semantics, then even case default parser will reject programs using auxiliary syntactic constructs. Indeed, when you compile a language, say lang.k, the tool will by default attempt to find the module lang-syntax and generate the program parser from that. If it cannot find it, then it will use the module lang instead. There are also ways to tell compile precisely which syntax module you want to use for the program parser if you do not like the default convention. See compile with the option --help. Another insightful thought to reflect upon is the relationship between your language's values and other syntactic categories. It is often the case that values form a subset of the original language syntax, like in imp in tutorial 2, but sometimes that is not true, like in our case here. When that happens, in order for the semantics to be given smoothly and uniformly using the original syntax, you need to extend your language's original syntactic categories with the new values. The same holds true in other semantic approaches, not only in K, even in ones which are considered purely syntactic. As it should be clear by now, K does not enforce you to use a purely syntactic style in your definitions. Nevertheless, K does allow you to develop purely syntactic definitions, like lambda in tutorial 1, if you prefer those. K runs some programs, such as those provided in lesson 1 of the lambda tutorial number 1. Note the closures, both as results in the K cell and as values in the store. Also, since variables are not values anymore, expressions that contain free variables may get stuck with one of those on top of their computation. See, for example, the free variable capture.lambda program, which gets stuck on z because z is free, so it cannot evaluate it. If you want, you can go ahead and manually provide a configuration with z mapped to some location in the environment and that location mapped to some value in the store, and then we can also execute this program. The program omega.lambda should still loop. Although we completely change the definition style of lambda, the semantics of the other constructs do not need to change, as seen in the next lecture.